Hi, Chris Good here. We're back with the solution to more practice t-tests number 4. So in this one, sleep researchers are deciding to test the impact, let's fix that typo, the impact of REM sleep deprivation, that's when people are most likely to be dreaming, on a computerized assembly line task. So participants are required to participate in 2 nights of testing. On the night of testing, EEG, electroencephalography, EMG, electromyography, and EOG, electrooculography, so you can tell when their eyes are moving. Those measures are taken. On each night, testing and participants are allowed a total of 4 hours of sleep. However, on one of the nights, participants are randomly awakened at various times throughout the 4-hour total sleep session. Testing conditions are counterbalanced. That's good. So half the participants experience REM deprivation on the first night, half experience it on the second night. After each sleep session, participants are asked to complete a computerized assembly line task. So the task is 5 rows of widgets slowly passing across a computer screen. Widgets missing a component that must be fixed are randomly placed in 1:5 ratio, and the number of broken widgets fixed by the participants is recorded. So compute the appropriate t-test for the data provided below. Based on this, I'd say that the number more fixed ones are better. So compute the appropriate t-test for the data provided below. All right. Oh, no, it's not. You know what? It's not broken widgets correctly fixed. It's broken widgets missed by participants. I copied this wrong. Broken widgets missed by participants. Okay. Compute the appropriate t-test for the data provided below. We're going to do a repeated measures t-test because these are the same people, which means that we need to compute different scores for each participant. So for number 1, we're going to subtract their control minus their REM deprived. All right? Then we're going to copy and paste and look at our mean difference score. Sample mean difference score is the average of all the different scores. Okay, that's what we're interested in. Okay. We'll use null hypothesis significance testing with the repeated measures t-tests, and so the null here is that in the population mean difference score is 0 because depriving someone of REM sleep doesn't do anything compared to the control condition. Doesn't do anything to the number of widgets that you miss as they're going by. For number 2, we're going to set an alpha of 0.05 and look up our t-crit, which means that we're going to need our n, which is just the count of how many different scores we have. Once again, that's 10. And our degrees of freedom, which is n minus 1. Okay, let's bold these and save them. And so t-crit at 9 degrees of freedom, if you remember before in a two-tailed test, alpha 0.05, 9 degrees of freedom, 2.262. If we, for some reason, we decided to do a one-tailed test, we'd look here for an alpha 0.05, here for an alpha 0.01, but we're not going to do that. We're going to do alpha 0.05, 2 tails combined, plus or minus 2.262. So this is plus or minus 2.262. Great. So now we compute t. If you've done a few of these, you might start to think, hey, I think I'm getting it. The repeated measures t-test is really pretty simple. You're only dealing with one group of scores. And those scores, the first step is we need to calculate the deviation of each different score from the sample mean difference score. All right, so we've got deviations for each one of our different score. Then we're going to square the deviations of each different score from the mean difference score. Just square those values. And that's how you get the squared deviations of each difference score from the mean difference score. So now we'll do the sum of squares. That's the sum of the squared deviations of each difference score from the mean difference score. And now we can get variance of the different scores. This is the sum of squares of the different scores. All right, so just align these real quick. Variance is always sum of squares divided by degrees of freedom. There's our variance. Now we can get the estimated standard error of the mean difference score. I don't know why it's not letting me do that. Okay. No spaces. That's all right. Whatever. There. Okay. That's just the square root of the quantity variance divided by n. And now we can compute t. T is only the mean difference score divided by the estimated standard error, the mean difference score. That's it. So we have everything that we need, and if those decimals bother you, oh goodness gracious, mercy me, we can get rid of them all, bring a few back. Now we have what we need to make our decision, which I'm going to write down here so I can go across the screen. Let's look at the graph, right? So our critical region's bounded by plus and minus 2.262. That means down here it's minus 2.262. Up here it's plus 2.262. So our observed t-value of plus 6.176 is going to be way over here. Now, I don't know how much area is under the curve beyond our observed t-value, plus beyond what the negative value would have been. But I do know that it's smaller than these two tails combined, which I know to be 0.05. So we know p is going to be less than 0.05. So we're going to reject the null, and we'll conclude that depriving participants of REM sleep significantly increased increased widgets missed in a computerized assembly line task. Compared with not. Well, what are we comparing it with? What did they do? They woke them up at random. So how about compared with random sleep deprivation? Okay, so now the reader of the sentence knows exactly what was done in the study. So we could move this around a little bit, make the sentence a little less clunky, right? We could say that compared with random sleep deprivation, depriving participants of REM sleep significantly increased widgets missed in a computerized assembly line task. We're not done with the sentence. We've got to report our t at 9 degrees of freedom was 1.506, and the p-value we already said was less than 0.05. Periods in the sentence, and we're done.